that you've learned the basic concepts of the JAX AI Stack, let's work through everyone's favorite ML example, MNIST, to deepen your understanding. We will, of course, be training a simple CNN with MNIST. First, we download the MNIST dataset from Hugging Face. The dataset's stored in Parquet format, so we'll read it in using pandas. We use wget commands to download the train and test dataset files. And these are commented out, but we include them here so you can see how to download the files if you need it. Next, we import the pandas library, which we will use for reading in the Parquet files. We then define the file paths for the training and testing data. And finally, we use pd.readParquet to read these files into pandas data frames named MNIST train df and MNIST test df. We're going to use Grain, the JAX native loader, to load the dataset. We define a dataset class that takes a pandas data frame as input. Inside the class, the dunderlen method returns the number of items in the data frame, and the dunderGetItem method fetches the item at a given index and converts it into a NumPy array. We also have a helper function called convertToNumPy. This function takes a data dictionary, extracts the image bytes, and then uses the Python imaging library, PIL, to open the image. The image is then converted into a NumPy array, normalized by dividing by 255, and reshaped to add a channel dimension. Finally, it also extracts the label and returns both the image array and the label array as a dictionary. Now let's instantiate our dataset class with the training and test data frames we loaded earlier. We'll create MNIST train and MNIST test objects. Next, we create a sequential sampler using grain.sequentialSampler. This sampler ensures that we iterate through the dataset in order. Finally, we create data loader objects using grain.dataloader. For both the training and test sets, we pass the respective dataset object, the sampler, and specify an operation to batch the data. We use grain.batch with our batch size and drop remainder equals true to create batches and drop any incomplete batches at the end. This sets up our data loaders to provide batches of data for training and evaluation. So far, we've only done normal NumPy and pandas stuff and set up Grain. Now we can define our CNN model using MNIST. The model consists of two convolutional layers, each followed by average pooling and ReLU activation. The output's then flattened and passed through two linear layers. This is a simple CNN architecture designed for classifying the MNIST digits. We instantiate our CNN model, and then we use MNIST.display to visualize its structure. This could be very useful for debugging and understanding the model's architecture. To quickly test our model, we import JAX NumPy and pass a dummy input of 1s to the model. This is before it's trained. This checks if the model runs without errors and produces an output. The output shown is an example of what you might expect before training. Next, we define the optimizer and metrics. We use the AtomW optimizer from Optax. Notice the new WRT equals NNX param argument in the NNX optimizer call. This is a key update in the latest version, the 0.11 version of NNX. It explicitly tells the optimizer that it should only apply updates with respect to the variables of type NNX param. This makes the optimizer's intent crystal clear. It will update our learnable parameters and weights, but ignore other types of state. Similar to the model, we use NNX display to visualize the optimizer setup. Here, we define the training and evaluation step functions. The loss function calculates the cross-entropy loss between the model's predictions and the true labels. The train step function computes the gradients of the loss with respect to the model parameters. It updates the metrics and applies the gradients using the optimizer. The eval step function calculates the loss and updates the metrics during evaluation without performing gradient updates. Both train step and eval step are decorated with MNIST.JIT for just-in-time compilation, which significantly improves performance. Now, we put everything together to create the main training loop. We iterate through the training dataset, and for each batch, we call the train step function. At specified intervals determined by the value of eval every, or at the very end of the training, we compute and record the training metrics. We then run the eval step on the test dataset, record the test metrics, and reset the metrics. This process continues for the specified number of training steps. Finally, let's run our train model on a few test images and visualize the predictions. First, we switch the model to evaluation mode using model.eval, and then we define a pred step function to get the predicted labels. We take a batch from the test dataset and use pred step to make predictions. Lastly, we plot a grid of test images with their corresponding predicted labels. This helps us visually assess how well the model is performing. You can learn more about JAX and the entire JAX AI stack with these coding exercises, quick reference docs, and slides. To watch the whole Learning JAX series, check out our playlist on YouTube. There's a growing community on Discord for JAX, and here's an invite link. And here are links to the docs for JAX, Flax, and the JAX AI stack. There's much more coming in our upcoming episodes on the rest of the JAX AI stack. So stay tuned, and don't forget to hit like and subscribe, and we'll see you soon.